The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to this webinar about new trends and die materials. The world of high-pressure die casting parts is changing fast. Growth of e-mobility and in particular structural parts has had a dramatic effect on die life in these new dies. Uddeholm has a proven record of success in the e-mobility sector, and this presentation sets out the problems and what tools deals from Uddeholm to select. My name is Ulf Weisen, and I'm Marketing Manager for voestalpine High Performance Metals in North America and moderator for this webinar. But first, let's make sure that you can hear us. Let's make a little audio check. So if we can go to the instructions. You should see this panel on your right side of your screen. And you can minimize it if it's blocking your view by pressing the orange button on top. And you can type in questions in this in the questions panel further down. So maybe you can just type in your name and where you are. Okay, I see one here. Okay, I see some more. We have from Spain. Good afternoon, I would say. And okay, Michigan, Wisconsin. Yeah, we have a good crowd here. Asia, Singapore here. Welcome. All right, I think that works. So we can move on. And I would like to say a few words about today's presenter, Richard Oliver. Richard has 25 years of experience as both tool maker and in sales. Since 2017, he's a global product manager, hot work at Uddeholm's AB in Sweden. He says about himself that my current role with Uddeholm's AB is to manage the hot work portfolio, which involves oversight of existing products and development of new materials for the global market. Our focus is on all major hot work applications, which includes high pressure die casting and general casting. Richard, hello, it's nice to have you here. We can all see you. How are you today?
Hey Ulf, yeah, I'm doing really well, thanks. It's still wet and rainy in Sweden, I'm afraid, so the weather's not much better.
All right, then a good time to do a webinar inside. So I leave it to you. Over to you, Richard.
Okay, thanks Ulf. Welcome everyone to this presentation. We're going to be talking about new trends in automotive die casting. Done this a few times. I remember I did this in Chennai in India last year, and I've done it in Germany and other parts of the world. So it's a lot of good content that's been well received. So let's see what you think of it. So it's important that we understand the modern trends in high pressure die casting, because part of my role as product manager for hot work here in Sweden is that we need to develop steels for the trends that we see in the die casting world. So it's incredibly important that we stay on top of this. And we're in a good place at the moment because we are ahead of our competition when it comes to structural parts for a steel that I will explain in a little bit. So if we look at the chart in front of us, you may have seen something similar. This is actually, the information comes from, this is our chart, but the information comes from a major OEM of vehicle manufacturing in the world, the top four. And they predict that by 2050, about 45% of all vehicles will be hybrids, and about 40% will be pure electric EV. And the rest will be made up of fuel cell, depending on how big that gets. But you might notice that the internal combustion engine drops rather rapidly until it completely disappears. But it only disappears as the only form of propulsion of the car. The actual internal combustion engine will continue in the hybrid till there's time that eventually hybrids are discontinued as well, and we have a completely electric fleet. But this is really, really good for die casters, for tool makers, for automotive companies in general, because the EV fleet has to now be built up from nothing, almost in many countries. It's still very low, single-digit percentage of cars sold, and the hybrid fleet is growing. So, of course, in the next 20 years, most consumers are going to be under pressure to replace those cars. The sales will inevitably go up. They have to, because the laws will be passed on old polluting vehicles. And the benefit for casters and tool makers and tool steel companies like ourselves is our parts are going to go up in casting, not go down. So that's the benefit of EV and hybrid. So for instance, in an electric vehicle, you will still have structural parts. You will have this in hybrid as well. You're obviously going to have battery packs in both vehicles again, and you're also going to have electric motors in both vehicles. So in a pure EV, you'll probably have 2 motors. You could even end up having 4 motors if each wheel was driven in the future. And all of those will be cast, so it's really, really good news for us. And if we just look at structural parts, one of the major US manufacturers that I visited a few years ago told me that they think about 30 to 40% growth is possible just in structural tooling on their vehicles. And if you put that into context, I'm very lucky in my job, get to travel a lot. I visited Ingolstadt last year in Germany to see Audi's R&D center, and they told me there that they think that the average Audi platform will be about 20% high-pressure die-casted structural panels. And that's just an average. They can go up, they can go down, but you can see this is spreading everywhere. It's even going to filter its way down to small vehicles in the future, so structural is definitely here to stay. If we look at this chart here, so that's structural, let's just talk about batteries for a second. So batteries are interesting as well. If you look at the chart on the horizontal going across to the left is the structural need increases, and the vertical is the size of the car. And then you obviously have, that's important for weight saving. So that's a point when weight saving becomes important. When you cross that, you need to think about maybe more batteries, lighting in the car and so on. So if you place in the first generation Toyota Prius there, that was a HEV, which is a hybrid electric vehicle. So these cars just need very small electric motors in comparison to today, and quite small battery packs. The battery packs were not structural. They were often just had a very limited range, so they weren't even that big. So there, the demands on the tool steel and the casting are actually quite low in comparison to where we are today. But today's a different story. So if we look at the hybrids, the plug-in hybrids you can get today, they're getting quite complex, very sophisticated cars, very desirable, in fact, with good ranges. So it's getting better and better every year. And these cars, the battery packs now are reasonably quite large. BMW, Audi, they all do pretty decent sized battery packs on their plug-in hybrids. And some of the battery packs are load bearing. Some of them need to be sealed in a crash, so they have to have some strength in them so that they don't split when the batteries run the risk, I guess, of catching fire in an accident. So there are restrictions there on the casting, which of course pushes up demand on the tool steel and in the tooling. And finally, if we go to the biggest electric vehicles that you can get, in the future, this is another trend, and this is where steels like Dybar were developed where they are today. So battery packs become part of the structure, just like structural tools themselves. So if you took the Porsche Taycan, for example, a big car that I particularly like, I can't afford it, but I like it. The floor pan is actually part of the structure of the car. So the battery pack itself, and the battery pack has to have some crash properties in crash. So just like a structural panel. So for instance, heat check marks on the critical surfaces wouldn't be allowed. So if you're going to have that, then you obviously need to have a tool steel that can cope with thermal fatigue and delay it as much as possible. And all of this technology is just going to filter its way down through to all the vehicles. Now, if we go back to where we are today with the internal combustion engine, as I said previously, I'm quite lucky. I get to travel a lot for my job in a normal year before coronavirus. On average, I do anything from 130 to 150 casting visits in a year. That's to all from OEMs all the way through to tool makers, the whole process chain. And this is just a snapshot of what I've gleaned over those years of what certain customers tell me. It's an average of what certain customers get. So if we assume that a clutch cover is being made, they come in all different shapes and sizes, so this is very general. But let's say a clutch cover is made on a 2,000 ton press or less. Then what we're saying here is I've seen customers that claim using H13, H11, 44, 46 Rockwell, around about there, they get anything from 80,000 shots to 150,000 shots. And you might notice that there's a variation, which seems a bit strange because you think, well, they're using the same hardnesses roughly and the same material, why is there a variation? But you can see the same in like an engine casting. So let's take a V6, for example. I visited a manufacturer in the US that says with their V6 engine, they sometimes struggle to get even 40,000, 50,000 shots. But in South Korea, I visited a major OEM where they said they get 80,000 shots on a V6 type die. So you can see the same variation there. And that variation comes down to several points. It's influence of the die design, the production variations, which are a pretty significant role here, the tool steel quality, which of course plays a big part, and also maintenance conditions of the tool, so how it's maintained and so on. And you're going to see that repeated a bit further on. If If we look at structural parts, and how do structural parts compare to that traditional clutch cover engine, internal combustion engine parts, they're actually quite bad. If you look here, the picture on the left is a longitudinal bridge structure, which I saw in Europe. And you can see the heat checking here is pretty bad. This is the thermal fatigue damage that you see on these types of parts. This manufacturer is very good. They have excellent process control, some of the best I've seen in the world. And even they have problems. So this is an H11 type tool steel. It's 44 of Rockwell, plus or minus 1. And you can see 30,000 shots just over. And the part itself has got heavy heat check damage on it as well. And that has to be ground out, actually. So in this manufacturer, they don't actually repair the die. They actually grind the part itself. And a typical production on the longitudinal bridge for this manufacturer could be anything up to 100,000 parts. But they start having to regrind it from quite early on. So maybe you see here 30, 40,000 parts and they're having to regrind. And it's the same with shock towers as well, just different levels. So if we look at shock towers, I've seen quite a few of these now in my trips globally. And if you think about a shock tower in itself, they're all different shapes and sizes, but they're quite complex panels. They're quite thick and quite thin in certain areas. Heat checking seems to be the main failure again with these, and it seems to come quite quick on some of them. And the die life there is just like with all the other stuff, depending on which manufacturer you're at. So again, I visited some customers that run shock towers and they can't even get 30,000 shots. In fact, they really struggle. I visited others where I'd probably say a medium average life is about 70,000, 60 to 70,000 before major issues. There's one market which stands out globally, and then that's Germany here. Germany has some of the best die life I've seen when it comes to high pressure die casting. They use an H11 type normally. But again, they're having to regrind the panels quite early on. So the total die life is probably quite good, but there's a constant reworking of the panels, which is of course very expensive. And interestingly, that tends to start around the 40, 50, 60,000 shot area, depending on how bad it is. So we've seen the trends and an indication of the type of challenges that you're going to face in these certain parts. So let's just look a little bit at typical die failure. So there are 4 that I'm going to talk about today. There are obviously a lot more than 4 failures, but these are the main ones you come across. There's corrosion, cavitation, and turbulence, but we won't cover those today. So soldering is a common problem. We work from the top down. Soldering is obviously where the aluminium or the aluminum wants to stick to the core pin. And this is normally, you find this in areas where the die is getting extremely hot and conformal cooling isn't used or can't be used or isn't used at present. Then we come to the big one, so that's heat checking thermal fatigue. Thermal fatigue is a cyclic problem. It's basically the extremes of the heat in the process and the coldest part and the gap in between the two. It's called the delta T, and that needs to be as close as possible to delay heat checking for as long as possible. And that's hard to do, and we'll go into that a little bit now. And then we have gross cracking. Gross cracking, of course, is a failure that everybody wants to avoid. No one wants a broken die. Unfortunately, I've seen several in my travels. It is still quite rare, but it does happen often enough to be a concern for most people. And gross cracking really is where you've overloaded the tool. It can be either process related or it can be mechanically related to something that's gone on in the process itself, press misalignment, and so on, sharp radiuses. And then we move on to erosion. So erosion is a hot wear, mechanical wear. It can also be chemical as well. It can be the type of aluminium that you're running, if it's high silicon. The velocity of the melt has a lot to do with this here, how fast your aluminium is coming into the die. And really coatings here or surface treatments are the long-term answer. And we've got some great examples to show you. So very quickly, just one page, we're going to cover each failure because we haven't got time to go into details. We could talk 2 hours, 4 hours about heat checking, for example. So heat checking, we'll just talk about how to avoid heat checking. What do you do to avoid it? As I said before, it's all about controlling the delta T, which is this variation in temperature from the highest to the lowest. That's the critical thing that you need to control. And you can go about that by various different things. So the injection speeds is one. So try to avoid excessive injection speeds, and I'll give you a rough rule of thumb in a second when we talk about erosion. Try to avoid excessive spraying. That kills dies, absolutely kills dies. I think at Eurogos a few years ago, a company called IV4 did a talk. They submitted a paper about spraying, and they said, I think it was something like 90% of all failure is down to spraying. It was quite critical, but spraying has a big influence, absolutely. Then think about the design, think about the heat treatment, and of course the maintenance. There's so many things that can influence heat checking. The tool steel, so if you look at demands from the material, which is what I'm here to talk to you about today, from a material point of view, we have to give the customer a material which has excellent hot strength, it has to have high ductility and toughness, and it has to have high creep strength. And what's interesting is if you don't have any of those three properties, then you're not going to have the performance in the material that you need. And if you look at the picture then, you can see exactly that's the same die that we saw before with quite excessive heat checking. And you can see there's actually breakout on some of the surfaces there of the tool steel. If we look at gross cracking, so I've included some pictures of investigations that I've done over my 5 years here at the mill. This is an All-Var Supreme tool that came into us. You can see the picture there on the right. Obviously, we've got a picture there of a close-up under the microscope. Gross cracking, you need to use the toughest material that you can. That's obviously a given. If you've got a gross cracking problem, you need to find out what's causing it. If it's not material related, but if it is material related, you need to use a better tool steel, absolutely. You also have to think about preheating. It might interest you to know that if you preheat even an H13 type material, you can double, triple the toughness in it in production. So preheating is pretty significant. And Dyvar is much, much tougher than an H13. So you can see what Dyvar is so popular. Again, control your cooling. If your cooling's all over the place, then you're going to reduce the toughness because it gets cooler, like I just explained with the preheating. And again, then you need to consider the design, the maintenance, and various other things, good heat treatment. If we just look at design there, this failed because of design. So the radius that you see here on the sharp corner, well, there wasn't really a radius, it was literally a 90-degree sharp corner. Try to avoid sharp radiuses. If the design says that you have to have this and you have good process control and everything else is really good and you just narrow it down to the tool steel's abilities to have good toughness, then we can recommend something like Dyvar, which is exactly what we did with this customer, Abel's Dyvar, after they had this problem. So that's what we need from our material. Material demands there on the bottom left, excellent cleanliness. Dyvar, for instance, is 100% pressurized ESR. We only use the latest furnaces now here to make Dyvar, and good toughness and ductility. If we now go on to erosion, what you can see here is a picture of a cast part. This is the left-hand gate entry on a heat sink part. And you can see here there's washout erosion there just where the gate is. Now this is a Dyvar tool. It has very, very good life. Actually, as you can see it now, this is 250,000 shots. But before, when it was just Dyvar, it did 150,000. When it was H13, it would have done something like 80,000 shots. So the company first went to Dyvar and then went to Dyvar with coating. And we'll go through the process now. So you have to consider the design when erosion is present, of course. If you've got a very, very thin gate with a lot of velocity coming through it, then you're definitely going to get washout erosion damage. So you have to consider the velocity and how much damage that's going to do. We tend to say if it's a non-vacuum assist die, 30 to 50 meters per second, that rough area. And if it's a vacuum die, then maybe 15 to 30 meters per second. Those are rough rule of thumbs. It goes up and down, and different manufacturers have their own standards, but that tends to be what we say works quite well. You really, however, have to use a surface treatment here. And of course, the aluminum matters as well. It's high silicon, and that's obviously going to affect what's going on there with the washout. So you have to protect the tool steel with a coating or a surface treatment. So here you've got the choice of nitriding or obviously Eiffel do a very good coating called Tigral that is quite successful in lots of dyes. But that coating and nitriding has to be able to stay on the material. So you still need a material underneath it, which has got very good high tempering resistance and hot yield strength. Because without that, the coating is not going to stay there. And then finally, we move on to soldering. This is quite interesting. This is an investigation I did about 3.5 years ago. This is a big H11 tool from Germany. Excuse me. And you can see here the tower all by itself. Look at that tower, completely isolated. What's interesting is the main gate is right in front of it. So you've got hot aluminium coming straight at that tower. Of course, we're getting soldering on the surface, which is what you can see. And of course, you've got to try and minimize the contact between the melt and the tool steel because the melt wants to bond with the tool steel. which is what soldering is. So you need to put a protective layer there. So that normally can be a coating, it can be nitriding, or even good lubrication counts as well, of course. You want to try to avoid too high dye temperature. We've got an extreme example here because this tower's got so hot, it's making it worse. And unfortunately, there's no conformal cooling in this tower. And that's where we lead on to really with good thermal regulation. If you use AM on parts like this that suffer this sort of problem, you can really, really improve your dye or your production rather, because then you've got this problem area doesn't become such a problem anymore. So AM really is the future. So the demands on the tool steel, at least for soldering, is excellent hot properties, excellent ductility and toughness for complex shapes. And here really we have two materials that you could use today. There's a steel called QRO90HT, which is a pre-hardened core pin material. Its hardness is 37 to 41 Rockwell. And that might seem like a low hardness, but it really isn't. Lots and lots of customers use it globally, including some major OEMs directly in their engine parts. And it works really well. You can use also the standard QRO90, which then can be hardened much higher. You can go all the way to 52, depending on the application. And it's got QRO90 has got the best thermal conductivity of any tool steel we make, and it's also got the best temper back resistance. So that's why it's so good. We also have dye bars. So for instance, I mentioned there about complex shapes. If toughness is an issue, then dye bar is a very, very good choice. So now we're going to go on to some tool steel solutions from Uddeholm. So if we take the longitudinal bridge tool, which I said about earlier on, we've now got quite a few customers globally for this type of part. So I can say with confidence that the main core cavity would be a dye bar, because if you want to delay heat checking and you also want a really tough material, don't forget there's lots of cooling channels in these dies. That's a major weak point. So you want a tough material as well. Then dye bar works really well. And hopefully in the next couple of months, we may even have some case studies if we're about to use them. So gates and screw areas, you can use whatever you want there, depending on the failure, to be honest. So you can use QRO90, maybe Unimax, maybe dye bar. It depends on what failure you're trying to solve. But again, additive manufacturing has got a big future here to keep the screw, biscuit areas where you want to control the temperature of the steel in that area. The core pins, we've just already covered it really. So QRO90 and additive. There are also other steels like Unimax, is very good for erosion resistance because it's high hardness. We'll cover those steels in a second. The main body insert could be anything from dye bar to H13. We actually do have customers in China where the whole die is made from dye bar. And that's where the dye bar upgrade came from originally. So dye bar was upgraded about 2 years ago now, and it comes from structural tooling. So we can actually say with confidence that dye bar was created for structural dies because that's why it was upgraded. And it comes from a project from a major German manufacturer that was making a big car in China, and they already specified dye bar and they wanted to use it in a bigger block. So we had to develop a new process to make it. We had to develop many new things, and we effectively created a whole new quality level for the dye bar by doing that, which I'll explain in a second. So let's talk about dye bar in a little bit more detail. If you haven't heard of this material, it's very, very famous. It's probably about 20 years old now. Like I said, it was upgraded just 2 years ago. You will now find it as the second highest rated material in NADCA, but the other material is a modified H11, which will not delay heat checking like dye bar does. So the beauty with dye bar is you get that extreme toughness, but you also get the ability to delay heat checking as well. You get very, very good temper back resistance with steel. It's like I said, it's an excellent ESR tool steel. It's actually all pressurized ESR furnaces now that this steel is made on, which would explain why it's so clean when you test it. It's very, very suitable for coatings and nitriding, and it's an excellent material for all complex dies, which is why it was selected for structural tooling. And that brings us back to April last year. So the upgrade was actually in 2018 in the mill, but we launched it in April. You can see the band A and band B for NADCA. So you've got B superior there, and then you've got the old dye bar rated at 14 foot-pounds, 19 mils. And obviously it's now upgraded to 25 mils and 18.4 foot-pounds. That's the minimum average guarantee from us, the manufacturer, to you, the customer, on the soft anneal delivered material. Now in NADCA you have to get 80% of the capability of the material. So in heat treatment that would be 20 mils. think it's just over 14 foot-pounds. The properties and the chemistry of the material then, so let's just talk about those three properties about heat checking, delaying heat checking that I mentioned before. You have to have temper resistance. And here we have the effect of 600 degrees C over time on Divar and Allvar Supreme. So this is our Allvar Supreme here, not competitor H13. So both materials start at 47 Rockwell, and you can see straight away Divar shoots off by itself. So when you get to 10 hours at constant temperature, Divar has gone from 47 to about 43 Rockwell, 44, and Allvar Supreme's dropped down to about 37. Okay, and then it stays parallel all the way. So that's one of the reasons why Divar gives so much better performance in heat checking. Another property you need is hot yield strength, which is what I mentioned earlier. So this is a tensile test at 550 degrees C. And you can see at 51 Rockwell there that Allvar Supreme has about 830 megapascal, and Divar has just under 1,000, about 970, 980. So again, big difference in hot yield strength. And finally, we come on to creep strength. So creep strength, again, this is a force, 500 megapascal, with temperature, 550 degrees C, and over time. And you can see, if we equate this to a core pin, so you can picture what's happening here a little bit more in your head. If you take a core pin at constant temperature, it's being heated up. Over time, that pin can start to move, okay? And what this is showing you is Divar takes much, much longer to start to deform. This is one of the reasons why it's used in extrusion, for example, for heat sink dies, because Divar doesn't flex so much over time and temperature. So in Allvar, it starts to go around about 150 hours. You can see there the curve. And in Divar, the same level is about 250. And actually, it doesn't really start to move until about 400 hours. So it's a significant difference against Allvar. And this is a really interesting chart. This shows you the heat checking resistance, how it goes up, even in H13. So you've got there 40 Rockwell to 52. And you see as the hardness of the material goes up in both Divar and Allvar, or in H13, the depth of crack decreases. So you can see on the right-hand side there, that's the depth of crack in microns. So let's pick a hardness. So let's say 44 Rockwell. So you can see at 44 Rockwell, Divar's got a depth of crack 20, so it's room temperature to 700 degrees C, 800 cycles, this test up and down. So Divar's got a crack of about 30, 40 microns deep maybe, and Allvar is about 100. So there's a huge difference between the two. But you notice that starts to get less and less and less and less as you go up to 52 Rockwell. But the problem there is, as you go up in hardness, the toughness, of course, you sacrifice toughness. And that's why NADCA tends to stick to 44, 46, because most dies, that's a safe area to be. So the question is, what happens to Divar once you go out of the NADCA safe zone, 46 Rockwell, and go higher, to try and get that better heat check resistance? If we just look at a case study, I'll answer that question in a second. If we just look at a case study to prove a point, because there's been lots of laboratory examples, this is a real life case. So here we have a 4-cavity die, left and right hand. And we have 2 cavities made of Allvar, 2 cavities made of Divar, both the same hardness, and they both done the same amount of production. And you see there that Divar, no heat checking at all on its surface, on the casting, and in Allvar, not a lot of heat checking. It's a good material, but you see there's much, much more heat checking than with Divar. So a great example there of two materials now they perform differently. If we take that to a customer that's more recent, this is confidential, so I can't show you any pictures, but I can tell you about it. So this is a customer in China that I visited where they actually specify Divar. This customer makes large castings. They actually have Buehler presses going all the way up. They tend to start from around about 2,500 tons and upwards. On all their presses from 3,000 tons and over, they actually insist on Divar for everything. Everything's Divar, because they know it's so much better at crack resistance than an H13. And what they do there, this is a battery for a bus. This is a bus battery. So the battery, the part itself is probably about a meter, just over a meter long, about half a meter wide, about, I don't know, about let's say 10 inches deep. And this box itself gets about 80 to 100,000 shots in Divar. And if it was made in H13, they were kind enough to tell me what they would expect, and they would expect 40 to 60,000 shots. And the reason they use Divar is they can guarantee to the customer 80,000 shots, which is what they need to do. But often it will run 100,000. So a great example of what Divar can do. Again, some more examples from my travels. So the auto gearbox here is from China. This is near Shanghai, and it's an H13, 4446, and they run die bar as well, 4446. They do first weld repair, so this is talking about when the die 13 is repairing. The first weld repair at 20,000 shots, and with die bar it's 45,000. So you can see there a big improvement in the maintenance life of the dies as well, not just total life. And they see there that the H13 would go on to do 50,000 shots and the die bar well over 80,000. So again, we see that figure in China of well over 80,000 shots compared to 50, 60,000 for an H13. In North America, the clutch cover is an example from North America. And here you can see a die which started in H13 at 42, 44 Rockwell. They get very different result. Obviously, the die is more challenging, so the life is less, but the performance increase is the same. It's a doubling. So they get 5,000 shots with an H13, and they have to weld repair. But with die bar, at the same hardness, they get 10,000. Again, completely shows the difference between die bar and H13. But then they used their own initiative. They went up from 46 to 48 Rockwell, and they got 15,000 shots. So you see a practical example of that higher hardness given with less heat checking as you go along. And they get well over 100,000 shots on that die. So I said I would give you an example of this higher hardness and what it meant. I'm allowed to name drop Corey here from Chrysler because I asked his permission whenever I do talks about this, because this was his idea. So I went to see Corey a few years ago, and he likes our materials. But he said to me at the time, we didn't relaunch die bar at this point, and I was trying to say to him, you know, it's really good toughness, and it's much better than it was in the past. And he said, I believe you, Richard, but what happens in a real die when we go over the 46 threshold? And he said, 8 foot-pounds is kind of where minimum I think I need. What would you get in die bar as you go up in hardness, and how does it compare to all of our Supreme? So that's exactly what we did. So you see here we took stock cross sections, so bigger cross sections at the mill. We heat treated them just to see what we would get. And you see there at 48 Rockwell in die bar we've got 17.7 foot-pounds, and in all of our Supreme we've got 10 foot-pounds. So a big difference between the two materials, and this just carries on as you go up higher. Now remember, the minimum level that he talked about was 8 foot-pounds. And we see here at 52, we've reached the limit now with all our Supreme. So you see you've got 7.7 foot-pounds there. But in die bar, you've got 11 or 12 yields, 15 yields compared to 10.5. So it's amazing. And of course, we're not about to start recommending you go at 52 rock on the dies. It wasn't for that reason we did this either. It was to show the potential of the material itself. Okay, how much tougher is it than H15? How did we do this? Well, as I said, we had a project with a major German car maker about structural parts. And in 2013, they came to us with this. And what you can see in front of you is 2 sizes from our stock standard range. So we've got 20-inch and 12-inch by 24-inch and 20-inch. And what happened is, by making these really big blocks for this customer, we had to improve the quality. But by doing that, we had to look at processes throughout the entire mill. So we actually improved the whole product by doing this, not just these big blocks we made. And this shows you what happened. So these are standard sizes. So if we look at the 20-inch by 12, in 2010, we were averaging around about 18 foot-pounds on that size. By the end of the project in 2018, we were averaging 21.4. And it's the same story for the 24-inch by 20-inch. What's really interesting is if you look at the very bottom scale there, that's the highest single result we achieved that year on all sizes. So all the die bar that we made, the highest result we got in 2010 was 20 foot-pounds. By the time this project finished in 2018, that had risen to 28 foot-pounds. It was the highest that we did that year. And I can tell you with confidence, because of what we've done here, those figures are even higher now. So the die bar product is fantastic. One of the reasons we've done that is investment in new equipment. So what you can see is a picture of 6 new automated heat treatment furnaces. This is for manufacturing soft annealed tool steel. And of course, this is taking human error out of the equation completely. So now we get a very, very consistent material. And of course, this benefits all of the products in our factory, not just die bar. But with die bar, we also looked at new heat treatment. We looked at new holding time temperatures, new process windows. Everything was looked at. And that's why we got this. So we're getting to the end of the presentation now. So we just look how this compares to some of our rival materials. Often I hear that a 2367 is superior to die bar for toughness. Blatantly not true. And just to show you that, if we take a 2367, a high quality one from NADCA, we can see here that this is a ductility test, so this is unnotched. And we can see here that we're getting 306 foot-pounds in 2019 when we tested it, and in 2011 it was 284 foot-pounds. But what you're not being told here is the machine's capacity is 450 joules. So we're actually starting to get a false reading here because the sample now is so tough, the machine's having trouble to actually break it. It's not breaking it back, it's just bending. If we look at the 2367, this is a good material made by a good manufacturer, and you might notice that their toughness, their ductility has dropped, but their quality hasn't gone down. We wouldn't say that for a second. That's the variation of the test. There's a plus and minus for all Sharpie and notch testing. And what you can say is it's the same, it stayed the same. But you can see there a clear distinction now between 2367 and Divar, and that's what we wanted to show you today. It's a very, very different material than 2367. If we look at Unimax here, Unimax is another tool steel that we make. This is like a son of Divar, so it's got more carbon in it, but it also benefits from a lot of the good ductility and toughness of Divar, not to the same level. There's a trade-off, but you get very, very good erosion resistance, hot wear resistance with Unimax, and its temper resistance is the same as Divar as well, but then you start at much higher hardness. Interestingly, we tested it this year in a forging application at 58, 56 Rockwell, and we got 201 foot-pounds in an unnotched test, 14 joules in a V-notch. And if you think, well, where does that sit then, Richard, if you ask me? Well, actually look at the 2367. So we've got here 201 foot-pounds, and in 2367 we've got 184, 222. So Unimax is probably somewhere in the middle of that, depending on the quality of the 2367. It's an excellent tool steel for delaying wear, erosion, so you can use it in gate areas, runners, if you can insert it. You can also use it for whole cavities if they're not too big. In the Asian market, Unimax is actually quite successful for telephones, for telephone castings. It's very popular there. It's a very, very good material. So let me come on to QRO90. QRO90 is a good material. It's about 30 years, in production. But it's the best temper back resistance of any tool steel we make. It's truly excellent. And it's that good that actually in certain cases where we've used Unimax and QRO90 together, if you think Unimax is at 58, QRO is at 52, eventually with time and temperature, the two will actually cross over. So actually in the long run, QRO90 has better temper back resistance even than Unimax. But of course, that's temper back resistance. Unimax would be better resistance. But this material is brilliant. So very good for corking. Very good material for corking. Allvar Supreme, or what can I say about Allvar? It's a very, very consistent, high quality H13. And I would argue it's the best in the world as a stock standard off the shelf. Very consistent. And don't forget, this material benefits from all the process improvements we've made here in general investments, heat treatment, and so on. So if you look at your Sharpie V values on your cert that you get for Allvar Supreme, you're most likely going to see figures well over 20 euros. Very, very good material. And the cleanliness is excellent as well. So how do we place these materials? Well, there's two there that I haven't mentioned, but we're focusing mainly on high pressure. But I put them here just in case there are some low pressure or gravity casters listening. So we do an Allvar 2M, which is an H13 type material, and we do Formvar. Now, Formvar is a non-ESR version of Divar, and also it doesn't have the same processes of Divar, so it's not as tough. But but it benefits from all of the hot properties that Divar's got. So high hot fuel strength, temper back resistance, and so on. If, however, we're talking about main dies, so this would be medium to, I suppose, good sized tools, but where long life isn't absolutely critical, then of course we've got Allvar Supreme. Allvar would be the die, say, over 60,000, 150,000 shots, depending on the size and application. And of course, for European listeners today to this talk, we've got Vidar Superior, which is an H11 modified, which is very, very tough, but it doesn't quite have the hot properties of an H13. So hence it's rated just slightly above. If we look at Unimax and QRO90, you can distinguish the two. You can say Unimax is for high erosion, high wear applications, and QRO90 for corkings. Very, very good for corkings, particularly if you use the pre-hardened version, QRO90 HT. And then finally we come to Divar. So Divar is the do anything material in effect. So for instance, it can be for dyes for 60,000 shots and higher if it's structural, because they're a much lower dye load. It can also be for long running tools if they're medium size. I showed you the example of the one that did 150,000 shots in the heatsink and went on to do 250,000 with the coating on it. So that's where our materials would sit. But if you want more in detail advice, talk to any of our technical staff. We can help you with that. So that finishes the talk. Bang on time. So Ulf, back to you for a Q&A.
Thank you very much, Richard. Very interesting. If you have to leave, just know that we have recorded this webinar, and if you want to watch it again or have a copy of a presentation, please contact Richard or Uddeholm USA, and they will arrange this and have a contact with you. And we will now take questions. And to do that, you just type in your question in the panel in your console, where it says questions. So let's see if we have anything coming in here. Okay, how much better performance will I get from Divar over an ESR H13 for heat checking?
That's a good question. Of course, it depends on the die and the size and so on, but you did see a repeat figure come there with certain dies. So say if an H13 does 60,000 shots, a Divar would tend to do 80 to 100,000. I would say the better figure to use would be what a toolmaker told me in Germany, where he expects at least a 30% improvement using Divar. We can't guarantee anything because we're not always in control of the processes, but that's what he would expect. And that's normally what I see, at least a 30% improvement in performance. And often you'll get way more than that if all the processes are working well.
All right, let's see if I have anything else. Your chart shows Divar tested at 52 Rockwell against H13 ESR with good results. So do you see this on real dies?
Sorry, Ulf, you just broke up there a second.
Okay, your chart shows Divar tested at 52 Rockwell against H13 ESR with good results. Do you see this with real dies?
Yeah, we do. I've seen many applications where Divar is actually used at 52 Rockwell. It depends on the application, but of course the toughness is there in the material. But certainly compared to H13, it's way, way tough. There's no comparison between the two, as we showed with the testing.
Okay. How does Divar compare with MS1? Not if that is a branded grade, maybe.
Oh, I'm not sure I know that one. Maybe there's a different. I can research it after this. MS1. That's one I haven't heard of.
It's follow up here. Maraging steel.
Oh, Maraging steel.
Maraging steel.
Yeah, Maragings are okay, but they're expensive and they don't have so much great erosion resistance, so they don't temper back so much. I know that Rovalma at Urgus last year we were talking about this, but they've been around for a long time, Maraging steels, and they've been talked about. I remember my old boss Ola used to talk about it. But yeah, of course for additive they're very good because they can be printed very easily, but the big dies, no comparison. The cost is just so extreme. Maraging steel, big blocks, and you're going to get erosion issues. It won't temper back, but you'll start getting erosion issues.
All right. Okay. Does Unimax offer better performance than 12367 for temper back resistance?
It's got the same temper back resistance as Divar. So because it starts up at high hardness, yeah, they temper back at the same level. So it's got better temper back resistance purely because it's higher hardness to begin with. But it would be parallel apart from the higher hardness, so they probably match each other as they go down.
All right, keep sending your questions. Richard is here for you, and we'll keep this open until we have answered all.
They're good questions.
So why is Divar so common in China, and do other markets use it in large volumes?
China's interesting because no one almost believes you when you say Divar is used so much in China, because obviously Divar is a premium material, but it's true. And The reason the Chinese use it is because it performs. They wouldn't use it otherwise. It can be specified. That's another misconception, actually, that they think most diver is specified in China. Most of it's chosen by the tool makers, or actually the OEMs. So even Chinese OEMs will use, the car makers will use diver. I actually think our biggest customer in the world is a Chinese automotive company, diver for engine parts. So that's why it's successful. It performs at the customer, and that's why it's chosen. So they really have done a great job in China of pushing diver so far forward. But it's now we're seeing that success even in different markets like Germany, for example. So a lot of OEMs in Germany are using diver, or they're trying it with structural tooling, and they wouldn't be doing that unless they had problems to solve. So that's a great market for process control. So it just goes to show that they still want improvements.
All right. I don't see any other questions coming in. Let's see here if I have any last minute. Nope. I think that's it. So thank you, Richard, and thank you all for attending this webinar. If you wish to reach Richard or an Uddeholm representative, we have on the next slide, here we have the contact information. Please visit www.uddeholm.com or call us in the United States and Canada on 1-800-638-2520 or Mexico on 52-442-689-5900. And of course, on the Uddeholm site, you can also find links to our international offices and branches. There will be a short questionnaire when we close and also in the follow-up email. So I hope you can take a moment to just let us know if you enjoyed this and what you want to hear in the future. There you can also let us know if you want to be contacted to discuss further. This webinar was recorded and we will make it available on demand. And with that, I wish you all, wherever you are, a good morning, a good rest of the day, or a good evening, a good night. So thank you, Viviette. Thank you and goodbye.